Hi, in this video we're going to be looking at a IIT JEE integral question. So if you haven't already seen this one before, you may want to pause the video and give it a go. Okay, so when looking at this problem, there's a few things which I notice immediately. First thing is the limits. Now, with these kinds of problems, it's all looking for the trick. Okay, it's all like an integration trick to help you answer these. Now, a limit like this, where one's positive and one's negative, sometimes suggests that a substitution of the form let x equal negative x sometimes suggests that that kind of substitution would be a good idea. Also, what else have we got? Well, this absolute value here, so this absolute value of x, that would also sort of suggest that this would be quite a good substitution to make. Apart from that, I can't see anything else. Okay, so let's just give that a go. So what we're going to end up with? Well, we're going to end up, after making a substitution, well, if we just differentiate, dx will equal negative dx. These limits are going to swap, in a sense. This is going to be negative pi on 3, and this will be pi over 3. Okay, so what's going to happen here? Well, we're going to have pi minus 4 x cubed on the top, and on the denominator we're going to have 2 minus cosine of the absolute value of x plus pi on 3. Okay, because obviously when we substitute x for negative x into there, it's just going to stay positive. Okay, and we've got negative dx. Okay, now one thing that I can see immediately is, well, here these limits are different to these two. They've just been swapped because there's substitution. But what we should know is that all of this is being multiplied by this negative, which has come from our substitution. And if you multiply an integral by a negative, well, essentially the limits can swap back over. So what's going to happen are these limits are going to return to those limits when we factor in that minus sign. Okay, so if we just factor that in, that's going to become back to being positive, that will be negative, and that minus sign is going to disappear. Now, if you haven't come across that before, do let me know and I'll explain as to why this has happened. Okay, so this is exactly the same integral here. We've just made a little substitution. Okay, so now that we've got the limits the same, a nice trick which they sometimes use is by, well, first of all, giving them a name. So let's call this interval here j. Why not? Okay, so this integral is j. Now this integral is also going to be j. Okay. Now, what is quite a common integration trick is to add multiples of these onto each other to make them, to put them in a form which is a bit more manageable. And we can see here that if we were to add this integral to this integral, now that they've got the same limits, well, we'd end up getting rid of this 4x cubed on the numerator. So if we do that, add the two j's together, so j plus j, we'll get 2j. That's going to equal the integral of pi over 3, negative pi over 3. So the pi's are going to add, so I'll have 2 pi, and on the denominator, well, the denominator is just going to stay the same. Okay, so 2 minus cosine the absolute value of x plus pi on 3. Okay. So, next, what do we want to do? Well, you may instinctively just want to divide by 2. I don't see that being a bad idea, so may as well give it a go. Let's divide both by 2. Now, well, I don't know why that's not wanting to delete. There we go. Okay, so the next bit of an issue is going to be the fact that we've got this absolute value sign here. It's not a nice thing to integrate, but a trick which you can do to sort of deal with this absolute value is to actually just have a look at the function that you've got. Well, the only variable that we've got here is this absolute value of x. So if you were to think about this function, it doesn't matter if these values were negative. They would just be exactly the same as if they were positive. So this is integrating between negative pi on 3 and positive pi on 3, which means that the integral between negative pi on 3 and 0 would be exactly the same as the integral between 0 and positive pi on 3. So what we can say is that this is going to be equal to, well, 2 lots of this, but the integral being instead between 0 and pi on 3. Okay. 2 minus cosine absolute value of x plus pi on 3 dx. Okay, next. Well, it's actually quite good that we've done that, and part of the reason we wanted to really get rid of these, well, part of the reason why we just did this is that, well, now our limits are purely positive, well, between 0 and obviously, well, greater than 0. So there's actually no point in even having these absolute value bars anymore, so we can just get rid of those, because all the values that this is going to take are going to be positive values of x anyway. Okay, so we've got something that looks a little bit more manageable now. Okay, well, I think we'll just treat this like any other integral at this point. Let's just make another substitution. I think letting x plus pi on 3 equal x might be a good idea. Okay, so you may sometimes be more used to letting this equal like another letter like u or v, but ultimately it's just a dummy variable, so me letting it equal another x is exactly the same. So this can sometimes just be, I prefer doing it this way, but you can do it however you want. So let's just scroll down a bit. Well, let's think about the limits. Well, first of all, I just want to factor this pi out, just because I think it looks a bit nicer if you do it like that. And our integral is going to be between, well, when x is pi on 3, we get 2 pi on 3. And when x is 0, we're just going to end up with pi on 3. So that's going to be our limits. I don't really need to differentiate this like how I did the first one, because if I differentiate I just get dx equals dx, because nothing really is going to change here. So I'm just going to end up with 1 over 2 minus cosine x dx. Okay, so this looks a lot more manageable. Now I would suggest if you're not really sure where to go from this point, that you look at what I'm about to show you, which is a thing called the tan x on 2 substitution, or the Weierstrass substitution. I think it's got its own Wikipedia page, so you can look at that. And what it states is that if we say t is tan of x and 2, well then cosine of x can be written in terms of this t. Okay, and it's a really useful substitution to make when dealing with trig functions, especially when they're on the denominator. So cosine of x is going to be 1 minus t squared over 1 plus t squared. Don't know why it keeps deleting it. Right. And dx, so these are things that you would commit to memory. You'd learn these. Okay, you can actually come up with these quite quickly when you know how, but that's for another video perhaps. So dx is 2 dt over 1 plus t squared. Right. Come on. Right. Okay, so let's apply the substitution to this. So we end up with 2 pi. Let's think about our limits. So when x is 2 pi on 3, well, over here I get, well, t is tan of 2 pi on 3 divided by 2. That's tan of pi on 3, which is root 3. When that's been the limit pi on 3, I get t equals tan of pi on 6, which is 1 on root 3, which you can write obviously as root 3 on 3, but I'll just leave it like that for now. And I have 1 over 2 minus, well, cosine x is 1 minus t squared over 1 plus t squared. And dx is now 2 dt over 1 plus t squared. Right, so again here. I would be tempted to factor out the 2 already, so we'll end up with 4 pi. Limits, let's put those in quickly. And let's deal with this denominator. So all of this is obviously multiplying this 1 plus t squared. So we've got 2 times 1 plus t squared, so we've got 2 plus 2t squared. And we've got as well this multiplied as 1 plus t squared, but the denominator is just going to cancel, so we've got minus times 1 minus t squared, so minus 1 plus t squared. So I won't write this out again, I'll just simplify it here. 2t squared plus t squared is 3t squared. 2 minus 1 is 1, so 3t squared plus 1. It's a bit bigger. Oops. Don't know why this is being a pain. Right, 3t squared plus 1. So, at this point, you should be quite happy because this is an integral which you should be familiar with. This is an integral of the form 1 over some constant times t squared plus another constant, which we should recognise as the arctan integral. So what we end up with is 4 pi times by, this is going to be arctan of root 3t divided by root 3, and that's between root 3 and 1 over root 3. So we're almost there. I can factor out the root 3, so I have 4 pi over root 3, so times in by. Well, putting in our first limit will be arctan of root 3 times root 3, which is arctan of 3. Minus, well, putting in our second limit, arctan of root 3 times 1 on root 3 is arctan of 1. And we're almost there. So there is actually a way to simplify this. There is an identity which is worth learning. I will come up with a proof for it if you wish, just let me know. And the identity is that arctan, sorry, apologies for my handwriting on this, arctan of x plus or minus arctan of y equals arctan of x plus or minus y, x plus or minus y, divided by 1 minus plus xy, xy. So, in this case, well, what have we got? So, let's rewrite it. So this will be our final answer for what j equals. J is going to equal 4 pi over root 3 of arctan well, in this case, x is 3, y is 1. And so it's going to be 3 minus 1, so 2. 1 plus 3 times 1, 1 plus 3, 4. 2 over 4, so that's arctan over half. Okay, and that's our final answer. Okay, thank you for watching, and if you have any requests, please let me know.